My name is Bill Wilcox, Oak Ridge, Tennessee, resident for 63 years, ever since, pretty much since the beginning of Oak Ridge. Can't imagine a better calling, a better career, better place to live, better people to work for, better people to work with, be associated with. Very important contribution to our country that I was privileged to have a very tiny, small part of. It was great.
Did you ever leave Oak Ridge once you moved here?
Never. Never. When General Groves took over the command of the Manhattan Project in September of 1942, the Manhattan Project had been formed in June. Colonel James Marshall was in charge, but in September they changed the command to Colonel Groves, and a couple of days later made him a brigadier general. And he took over, as Stan Norris and many other people have said. Groves was really an indispensable man. Looking back on it, I can't imagine the Manhattan Projects doing what they did as soon as they did, as well as they did, without a hard-driving, absolute taskmaster in charge like General Groves. He took over in September of 1942, and although he was an expert in construction, just finished building the Pentagon and bases of one kind or another all over the U.S., he didn't know beans about atomic energy or about building an atomic bomb. And so for the next couple of months, in addition to picking out the site here in East Tennessee to build these huge plants that Vannevar Bush and James Conan told him we're going to have these big plants. He didn't have any idea of what was going to go in them, but he knew that it would take lots of space and there'd be lots of people. But during those first 2 months, General Groves had the job of going around talking to these university scientists about how this incredibly difficult job of separating uranium-235 from U-238 could possibly be done. And I'm sure he was bewildered, and I'm sure when he starts talking to these PhDs, college professors who can't talk without going to a blackboard and starting to write differential equations on the board and explaining how you integrate them. It's just amazing that he just didn't let that overpower him, but he listened to him. And his job in those next few months was just incredibly difficult. He went to the University of Virginia and talked to Jesse Beams, Dr. Jesse Beams, a very Virginia gentleman, a brilliant physicist, and a very easy person to talk to. But Jesse Beams had been separating uranium isotopes using gas centrifuges, very, very complicated mechanical long tubes spinning at high speeds with very complicated bearings at the top and the bottom. These things almost 4 feet long, but a lot longer because of the bearings top and bottom. And Beams is the only person of all the ones that he was going to talk to who could say, hey, I've separated about a gram of uranium-235. And this was a tremendous accomplishment. So Groves was very impressed with the gas centrifuge as a possibility. Then he goes to Berkeley, California, and he talks to Professor E.O. Lawrence, who is Mr. Enthusiasm about by gosh, I'm quite sure we can do this using a modification of a cyclotron that I developed. And he explains this to Groves, and I'm sure Groves, when he saw this huge cyclotron, these big magnets and these tubes and devices, I'm sure, I'd love to know what he thought. But he hadn't separated anything to amount to micrograms of U-235, but was enthusiastic about it. And then he goes to Columbia University and he talks to Dr. John Dunning and George Pegram, and he gets the story about this gaseous diffusion process. And it's just amazing to me that to think that this hard-nosed construction engineer is going around trying to figure out which one of these he's going to bet on, because President Roosevelt made it very clear that we were going to have an all-out effort, and we were going to get to the bomb before Germany did. And if anybody could make one of these darn things, he wanted to make it. And Roosevelt was convinced, Vannevar Bush, his science advisor, was convinced at this point of the game that it would be possible if we had a real all-out effort. But Groves now is in the position of saying, oh, golly, Ned, everybody has told me, yeah, this is a possibility. There was another guy that he talked to, Dr. Philip Abelson, about the idea of using very, very long columns, which are filled with uranium hexafluoride, and on the inside you heat it with superheated steam, and on the outside you cool it with river water. This is a process called thermal diffusion. So that was in the mix too. But Groves very quickly said, well, that one is no good. That one is just too complicated. And we don't know enough about it yet. So this problem that he has, you see, in December of '42 is which one am I going to bet on? And there are 4 horses in the race, and none of them has won a race before. They haven't even run in a race before. So imagine the problem that he had. But he was a decision maker, and he was determined, by gosh, they were going to do it somehow. So what they did, first of all, they ruled out thermal diffusion. And secondly then, after they went and looked at a pilot plant that Jesse Beams's people had built in New Jersey, it was the only process that had even gotten to the point where they could build a small pilot plant. And they did that. And they had industry come in. Westinghouse designed the big centrifuges and built them, and Standard Oil of New Jersey put this pilot plant together in Bayway refinery of theirs in New Jersey, and had actually operated it. Numbers of centrifuges working together to separate 235. It was the most advanced of any of these 4 horses. The only one that was really trying to do it. But they had, with the centrifuge, the way to increase the separation is to run them as fast as you can. So you do that. You run them as fast as you can without them blowing up. But occasionally they blow up. And the Bayway Refinery, they'd had experience with the machines blowing up. They're in casings. They don't kill people or anything. It's a failure, but it's not a disaster. But when Groves looked at the pilot plant then in December and saw all these machines working, he decided that this was a mechanical nightmare, and just couldn't imagine building a plant that had maybe 10,000 of these very, very nice, beautiful machines whirling around, spinning, and so on and so on. And the thought of running 10,000 of them just said, okay, that horse is gone too. That left him with 2 horses. And one of them was Professor Lawrence's cyclotron-based process, and the other was Dr. Dunning, Columbia's gaseous diffusion process. And so at the end of December, Groves made that decision. We're going to go with Lawrence's process. That's probably the best bet. And that's what turned into the Y-12 plant. Lawrence didn't use his cyclotron, which the magnets are lying down like this, and you have the atomic beam coming around, spinning around inside. He invented a new machine he called a calutron. Cal for California and tron for cyclotron, U for university, calutron. And the magnets stand up like this. And the atomic beam does the separation, goes up and down. And Y-12 then, Lawrence was delighted that his process was chosen for the first operation. He had built one of these gadgets and run it all through December and produced something like 100 micrograms of uranium-235 separated, slightly enriched, not completely fully enriched, but very highly enriched. But, you know, 1/10 of a milligram, a smidgen. And here Groves is saying, okay, we're going to build this plant at Y-12. Now let's get somebody to operate it. And again, this is an example of the brilliance of the Groves's. Yes, by the end of December, he had, with his military policy committee and his scientific advisors, they had decided on the horses that they were going to put in the horse race. And those 2 were the electromagnetic process based on the University of California cyclotron work by Professor E.O. Lawrence, and the gaseous diffusion process, which had been under research and development at Columbia University since early 1940. And the reason that they considered 2 horses is because, frankly, even though Professor Lawrence was very enthusiastic about the possibilities, there were still many questions, theoretical as well as practical, and very many engineering questions. So here we have a situation where they're not even positive that in the laboratory it'll work. They have never done a pilot plant, scale-up operation to see if it would work, let alone build any. They didn't even have any idea what a production machine was going to look like. So Groves, under this pressure to be certain that we got there before Germany did, and allowed to hedge his bets by President Roosevelt, who essentially had given him a blank check. He said, I'm going to build plants using both processes. I'm going to hedge my bets. There were a number of questions about gaseous diffusion also. They didn't have a barrier that was at all practical in December of 1942. So the whole Manhattan Project, you see, was the motto that they used all through the 43 and 44 were, an effort will be made. And what that really signified was, we're going to try do our very, very best. But is entirely different than we're positive that we can build one of these things. So having decided on which horses are going to run by December, then Groves turned to the crucial question about who are we going to get to do this. Now, he couldn't expect that Professor Lawrence would come in here and head up an engineering effort to build this plant, and so on, gaseous fusion. He had to get an industrial empire put together real fast. And he and his advisors were smart enough to know that at both Y12 and at K25, the kind of companies that you needed were companies experienced in chemistry and chemical engineering, companies that knew how to build big plants. For example, gaseous fusion, he enlisted Union Carbide, whose Carbide and Carbon Chemicals Corporation was experienced in handling gases and petroleum products and making things out of organic compounds, building big plants that could distill various organics, oil, and the Linde Chemical Company was part of Carbide. Linde was the primary company making liquid nitrogen and experts in handling gases. So Groves went to Union Carbide and said, we've got to have you come in and help with this critical operation of running this plant when we get it designed and when we get it built. In December, on Christmas Eve Day, in December of 1942, he sat down with the officials of Tennessee Eastman and Eastman Kodak Company and twisted their arm all day into running the Y12 plant. He felt that here is a company that understands chemistry, chemical engineering. They had just built an RDX improved explosive plant for General Groves. He knew Tennessee Eastman. They told him all day long, Christmas Eve, 24th of December, they told him all day long that they just couldn't do it. They were stretched too thin doing their own operations and this RDX plant that they just built for him. It couldn't do anything else. And Groves said, this is a plant that's going to do something. If we're successful, it might end the war. And this is the kind of argument that he used. They asked him, of course, where it was going to be. He said, I can't tell you. He said, what is the process going to be like? He said, I can't tell you. It's secret. And so on and so on. So, but he appealed to their patriotism and the importance of this particular task and what it would be like. We have the memoir that James C. White, who was the president, wrote and describes this day with General Groves. He says that, well, finally he asked General Groves, well, just, can you tell me how many people we're talking about? And Groves said, well, I think probably about 1,500 technical people or something like that, maybe 2,000 total employment. And of course, 3 years later, Y12 was 22,000 people. At that point, Groves, because of his conversations with Lawrence and his conversations with Oppenheimer, had a very, very much smaller idea of what the size was going to be than it turned out. It wasn't Groves's fault. It was a combination of things. The productivity of the machines turned out to be a little lower than what Lawrence had expected, so they had to build more of them. But the main problem was that when Oppenheimer and his scientists got together, finally, in April of 1943 at Los Alamos and started to really go to work calculating what the critical mass would be, that they have to, how many pounds of 235 you're going to have. The numbers started increasing. And instead of just one critical mass, they knew that they're going to have several critical masses in order to be sure that the bomb worked, and so on and so on. So that right at the beginning, and back in December of '42, when they were talking about this, and Groves, after he had gotten Tennessee Eastman to sign on, and in January, after he'd gotten Carbide to sign on, and earlier in December, when he'd gotten DuPont to sign on to build the graphite reactor plant here at Oak Ridge, after he had lined up his main contractors, he went to his construction contractor, Stone and Webster from Boston, and said they were going to build 3 sizable institutions here in this Oak Ridge area. We're going to need a town for these people to come live in. And they said, well, okay, how big? And he said 13,000 people. And that, you see, was where he was in the start of 1942. A year later, he changed it to twice that many, and a year later, he changed it to twice that many, and they ended up, you see, with 75,000 people in 1945. But it wasn't bad estimating. It was just that as the physicists gradually got more and more information, started to do a little experimental work, instead of just calculating on blackboards, the critical mass, the amount of material grew larger and larger, so therefore the plant grew larger and larger, therefore the town had to get larger and larger, and so on. So as we went into 1943, as far as the research and development goes, it's going on full blast at all these institutions around the country. The companies that he had enlisted started getting into work with architect engineers with the design of these buildings and processes. And then in the spring, each one of these companies, seeing that they're going to need people to come and do the grunt work at the plants, start fanning out to all the colleges and universities in the U.S. And trying to grab from the graduating classes people with degrees in chemistry, chemical engineering, physics. Of course, the Army had grabbed a lot of them, and a lot of the male graduates had signed up to go fight in the war effort, because everybody at that time was, the World War II was the key part of all of our lives then. And all of us were wondering what in the world we could do to help win the war. A lot of us thought we ought to join the Army Air Force or do this or do that. But the graduating class that spring, which I was a member of, we went to I went to a American Chemical Society meeting in Detroit, Michigan, from my college, Washington and Lee, in Lexington, Virginia, where I graduated in April, or I was going to get out in May, I guess graduation, but I went in April, and we signed up for the Employment Clearinghouse and posted our resumes on a big blackboard along with people from all over the country, chemists. This is the way we got our jobs in those days, American Chemical Society. And I ended up with requests for 18 interviews. People were really hiring everybody. Part of it was because of the war effort required technical people of all kinds of skills. But the first interview I had was with H.J. Heinz in Pittsburgh, and a dear old gentleman, Dr. Almy, I'll never forget him, a real nice grandfatherly man. He wanted me to do ascorbic acid analyses on batches of tomatoes that they were going to make their ketchup from, and how important this was that it be uniform from batch to batch. And I listened to him for a long time. and I finally told him, I said, it sounds like a very nice place to work, and I'd sure like to work for you, but I feel like I need to do something for the war effort. And he said, I understand that, young man. I went on to my other interviews and accepted an interview with Eastman Kodak Company, who, but when I look back afterwards, after the war, and find out what was going on, begin to appreciate the complexity of the Manhattan Project, I look back and I think that if I had accepted any one of a dozen of those 18 interviews, I would have ended up working on the Manhattan Project. Iowa State was doing uranium feed research. University of Chicago, University of California. There were people all over the country were in the marketplace, and they just scooped up the youngsters from the class of 1943. The Eastman Kodak guy that was interviewing me gave me the General Groves treatment. I asked him, where will I be working? Will I work for you guys in Rochester? No, won't be working in Rochester. Well, where will I be working? Well, I can't tell you. And so on and so on. Well, what kind of work will I be doing? Well, it's going to be war work. But I said, what kind of chemistry? Will it be organic or inorganic or physical or what? No, can't tell you. It's secret. It's secret. It's secret. It's secret. I didn't see anything to object to, so I said, okay. I knew it was a good company. And so along with about 50 others from that graduating class, I went to Rochester, New York to report for employment in May of 1943. And of course, looking back, there wasn't anything here at Oak Ridge Reservation. They were still tearing down farmhouses, putting in 300 miles of roads and railroads and infrastructure. They were the only building that was being built in May, almost finished, was the big federal building, the administration building, Castle on the Hill. That was well underway. It was finished in June or July of '43. But as far as Y-12 is concerned, it was swarming with people. And even though they didn't have the final designs for the calutron machines, they were building the buildings. Somebody had gone out to Lawrence's place and said, well, how big are these things going to be? Well, we don't know. Well, is it going to be any bigger than that cyclotron standing up on its end? No, probably won't be. So they had actually designed a 425-foot long building, so many stories and so on, and they'd started building these things just as fast as they could. General Groves said, we'll just save space inside, make it big enough, make it strong enough, estimate this and estimate that. And the engineers did a fine job. And when they got around to putting the machines in them, the buildings were just pretty much the right size. And but that's why we all were shipped up and reported to work in Rochester, New York. And we spent the summer up there in locked laboratory rooms doing research on uranium chemistry. When I reported to Rochester the first day, we lived downtown Rochester, right in the middle of the city in the YMCA, and we were all just out of school. All of us were in the same boat. We we'd been going to school, paying our way for years, and all of a sudden we're working for a living and getting a paycheck every 2 weeks, and we felt like we were doing real well. 37 bucks or something a week. It wasn't much, but Kodak Park's research laboratories, big, beautiful research building. They were still doing all of the Kodachrome processing in the first floor of Kodak Research. And so the building was just full of scientists doing very, very elegant chemistry work. It was a fine place to work. They didn't tell us any of their secrets, though. Their proprietary secrets, Kodachrome finishing, the way they recoat, the way they control the thickness of the emulsion on film, which controls everything, and the different layers, all of that stuff, all of that information is proprietary information. But as far as keeping things secret, that was just as secret as what we were trying to do, so that it sort of came natural to all of those people that we kept our doors locked and then didn't tell anybody what we were trying to do. When I got there, the welcome was by the vice president of research. Nice three-piece suit, black tie, very distinguished-looking gentleman, Dr. James G. McNally, and Secretary finally ushered my lab buddy Paul Blakely and I into his office, and he said, Mr. Wilcox, Mr. Blakely, welcome to Eastman Kodak. So we're pleased that you saw fit to join our company in this tremendously important war work. He said, as chemists, you'll have to know that you'll be working this project with a substance called uranium. That is the last time that you will hear that word, or you will speak it until after the war. And if you are ever heard speaking the word, you will be subject to discharge from our employment immediately, and very likely persecuted by the United States government, prosecuted by the United States government, and may end up in jail. Is that clear? Boy, I'm sitting there, my knuckles are white, and I'm grabbing hold of the chair. Paul said, yes, sir. I said, yes, sir. He didn't smile at all. He said, you'll call it a Tuballoy, codename, and use the chemical symbol T. And you learn to talk about all of its compounds and all of its reactions as Tuballoy compounds, such as hexavalent ones, call them tubinyl sulfate or tubinyl chloride, tubinous oxide for TO2, and so on and so on. Is that perfectly clear? Yes, sir. Yes, sir. And that's the way it was. We used code names for the whole thing. We worked all summer long developing, understanding uranium chemistry. There were no textbooks. You couldn't call in a consultant knew all about uranium. You couldn't. We really learned uranium chemistry from the ground up. Here I am, 20 years old. I was a little younger than most of the guys. When we went out to a bar for lunch for beer, I was the only one that couldn't ever get anything. I was embarrassed to death. But what I'm saying is that even though we were 20, 21, 22 years old, we ended up at the end of the summer, in the fall, we knew more about uranium chemistry than just almost anybody else, except people that had been working on the chemistry, say at Columbia or maybe at Iowa State, some in California. The first building, chemistry building, was finished at Y12 in October, and we all ended up coming down here. All summer long, we kept trying to find out where it was we were going, and all they would tell us is, well, it's a place somewhere in the U.S., and we all called it Dogpatch. Some people call it Shangri-La. And how we got the name Dogpatch, I don't know. That, of course, is out of the Little Abner cartoon strip, and it's sort of a hillbilly thing. And that might have been a giveaway, but none of us ever even thought about it being, when people started thinking about where Dogpatch was, they were thinking Arkansas rather than hills of Tennessee. October, the day came when they said, "You're leaving. We're going to the site," and gave us train tickets. Or one of the guys that I'd met up there that summer had a car, very unusual, and I hooked a ride. We piled in his car and came down. I'll never forget the day we got here. We spent the night in Cleveland and drove on down and had to spend the night in Knoxville and then came out the next day. So we hit Oak Ridge in the daytime, Clinton Engineer Works, of course, and we had passes and got in and went to TEC employment office, which was down in the middle of town. And my neck hurt at the end of the day from shaking my head all day long. It just couldn't believe it. It was just an amazing place. It was farmland, you could tell that, but there was construction going on everywhere you looked. Trucks and people just crawling all over the place, hammers and banging, saws, wooden structures going up everywhere. Roads, road machinery, nothing was paved, and there weren't any sidewalks, all boardwalks. Somebody, bless their hearts, when they cut down all these darn trees to put up a building or something, they had a sawmill, and they used the lumber to make sidewalks, boardwalks for us. We had miles, 160 miles of boardwalks all over town. It was just an amazing place. There's so much going on. There weren't any signs except for security signs. Keep your mouth shut, loose lips, sink ships, and things like that. But there weren't any signs on buildings. There were just numbers, code names and numbers. And dormitories were M1, M2, and M3, and the other dormitories were W1, 2, and 3. It took us about 24 hours to figure out it was men's and women's, and we were thrilled to count them up at the end of the day. A bunch of us got together and said, "I've counted 10 women's dormitories and I think 5 men's dormitories." And we said, "Well, by gosh, that's about the way it ought to be." And they were all chock-a-block full too, 150 gals or guys in each dormitory. The buses had these strange destinations. They didn't tell you where they were going. They had X10 or K25, Y12, town site, East Village, West Village, and that's it. But everything else was just numbers or some kind of strange coding. It was a remarkable place. It was Army cafeterias where we all had to eat, and we all ate together. They had a big recreation hall. We all went up there. They had bowling alleys. This is when I first got here. And those first 15 dormitories expanded to 90 in a couple of years. 90 dormitories all over the place for 13,000 single people. The bosses that came in from the companies, as you might imagine, from Carbide and from DuPont and from Eastman Kodak, they weren't their top management people, of course. They were their younger middle management people that were willing to get up and go somewhere to do this. And so our, and I was in the grunt corps, what would be the first line supervisors after a while. But those people, the professionals from Carbide and from DuPont and from Columbia, Eastman, Kodak, those were old folks. They were hell's bells. They were 30 to 40 years old, and lots of them with little kids. In 1945, the average age of the people in Oak Ridge was 27 years old. Can you imagine? 75,000 people. So this was a very young place. And we had everything the Army provided. Leslie Groves again, he did not want an Army camp here. And this was not an Army camp. There were 1,500 soldiers here out of the 75,000, but not like you see in an Army camp. I mean, no big parade ground, not so people marching around and so on. And Groves realized that it was important to have a feeling of a community where these scientists and engineers and top managers and their spouses and their children would feel at home, not like they were just off in a terribly temporary community. He wanted it to have a feel of a normal town, and that's why they did such a beautiful job on the layout of the community. And people were relatively happy. It was a great place to raise kids. And they had neighborhood schools and neighborhood shopping centers. There were buses here, loads of them, but most people could walk to a shopping center where there was a grocery store, a beauty shop, a barber shop, laundry, little strips, 12 of them all around the town. And there were 9 elementary schools, so most kids could walk to school. So the town was really a remarkable place. Ground was broken for the Y-12 plant in February of 1943. And in the same month, they broke ground for the X-10 graphite reactor, which was to be a pilot reactor for the manufacture of plutonium, teaspoon-sized quantities of plutonium, so that the chemists could do research on the processes that had to be used at Hanford, Washington. At Hanford, where the plutonium, big plutonium reactors were going to be making the fuel for the second atomic bomb. The question was, we know how to make the plutonium by a nuclear reaction, but the question is, how are we going to separate that stuff from all the uranium fission products that are made? And so far, the chemists had just had microgram quantities. So they wanted to get their hands on gram-sized quantities so that they could really do the research and develop good processes. So both of those facilities, the ground was broken in February of 1943. And all summer long at Y-12 plant, they built these enormous buildings for the machines that they hoped they were going to be able to buy and install. And sure enough, by the end of the summer, they started actually installing the calutron machines. These are complex physics machines. And at Y-12, they ended up with 1,152 of them. 864 were great big ones, about 8 feet tall, and the rest of them, were 350 or so were smaller machines. The reason for the big ones and the little ones is that in the calutron process, it's a very powerful process as far as the amount of separation that you get, but you do have to do it twice. You can't get pure U-235 in just one pass through a calutron. So you have to have those two sizes. One of them we call alpha calutrons, one of them we call beta calutrons. These alpha calutrons, the way the separation takes place is that you have an electromagnet, a strong electromagnet, strong magnet, and it's big. It's about 8 feet tall. And then in between these magnets, you put a vacuum tank, pump it out, high vacuum, and you vaporize some uranium, uranium tetrachloride specifically, and you vaporize it. Heat it up to about 400 degrees, and it boils out of this tank down here at the bottom. And then you bang it with an electron stream, which knocks an electron off of the UCl4 and gives it a positive charge. And then that stream now has a positive charge so that you can accelerate it by putting a high voltage out here, and you can accelerate that so that the stream comes zipping out. Well, if you didn't have a magnet, that stream would just go in a straight line until it stopped by something, bumps into something. But with a magnet, it bends that stream in a hemispherical semicircle. And so these charged molecules go zipping around in a long circle. And up at the top, you see the heavier ones have taken a larger diameter course than the lighter ones. You think about a whip in an amusement park with the people that are heaviest in the seats, you know, those cars are going to go out farther. Or these airplane rides where you ride in buckets around and the heavier ones go out to the top. So that up at the top you have a little separation, maybe 1/4 of an inch between the 235 stream and the 238 stream. And so then you put a pocket up here with slits in it, and the 238s go in one slit, the 235s in another. Sounds simple. And but the beams aren't very sharply focused, aren't completely sharply focused, and by the time they get up there, they're spread all over the place. So you don't get complete separation, and you don't get a very pure cut. The stuff gets spattered all over the walls, and you have to get in there and scrape it off with acid or something, and then turn it over to the chemists to get it all pure again, to stick it into the beta calutrons. That's why I was there. I was in beta chemistry, and my responsibility, along with the other people I worked with, was to take this alpha product out of these pockets and on the sides that it spattered over, and take it into the laboratory and separate it from all the other junk that we had to leach off the walls. If they were stainless steel, for example, and it came to us, the uranium 235 was all mixed up with iron and copper and nickel and molybdenum and so on and so on. We had to make nice pure stuff, get it back to uranium tetrachloride to put into the beta calutrons. So imagine now you got 864 of these all working, and it's a batch process. You put so much uranium tetrachloride in here, and you run it for 3 or 4 days, and then you take it apart, and you have to clean everything up and start all over again. So this is why it took so very many people, you see, thousands and thousands of people. And unlike gaseous diffusion, which is just a continuous process, and you turn on the electricity to all these pumps, you know, and you get that stuff in there and it just whirls around and you just stand back and watch it and open the valve out here and pull some stuff off, which is far less labor intensive. But Y-12 was an incredibly successful operation after the first months when it was just agony. Everything went wrong that could go wrong. The first calutron started up. I said that they broke ground in February. It's hard to believe, but the first machine started in November. It was just incredible. But it shut down almost immediately. Sparks, electrical shorts. Groves just went berserk when he heard about it. He just, you know, he was thrilled that it was getting started. But the place just, you know, just, and this is not a lot of calutrons, this is 1 or 2 or 3 or 4 of them, but they shorted out. They found out that the magnet gaps were too close together, and there was dirt in the oil that was causing these short circuits. People hadn't put in a careful enough cleaning system, a filtering system to clean up the oil. He was just furious. They had to rip out the machines and send them back to Los Alamos and rewound the magnets. It was dreadful. I need to interrupt just to tell you quickly a fascinating story about these 8-foot magnets. And that is that, of course, the way you make an electromagnet is you wind the copper wire around a iron core, and then you run current through the copper wire, and that generates the magnetic field. But it was clear in 1942, long before the that can't be right. Let's see, it must have been 43. Yes, it was 43. It was after they'd already decided to build Y-12. That's right. It was in the summer. They were building the buildings, but they were getting ready to build the calutrons and the magnets for it. And somebody started calculating how much copper it was going to take for all these magnets at Y-12, and realized that it was going to shut down and have a major impact on the war effort if Y-12 corralled all that copper. Now, we had the top priority in the country. Groves had gotten a AAA priority, and he could have just said, we have to have it. But then we'd have problems with electrical motors for airplanes and airplane engines and tanks and tank engines and so on, so on, so on. It would have been a disaster. And somebody, I wish I knew who it was, but somebody had this brilliant idea and said, look, silver is a better conductor of electricity than copper. We can make a electromagnet very, very nicely out of silver. And this plant's going to be under guard behind big fences. Everybody that's going to be working with it is security cleared and is trying to do what they can for the war effort. Why don't we just borrow some silver from the treasury? They've got ingots up there by the kazoo backing up the silver currency, the paper currency, silver certificates, and it's just sitting there doing nobody any good. So they went to the Undersecretary of Treasury, Bell, Colonel Nichols, in August '43, and explained it to him, and he said, why, certainly, that's we'd be glad to help the war effort. We understand. You guys will give it back, take good accounting for it. Oh, yes. And he said, well, how much do you need? And Nichols said, well, somewhere between 5,000 and 10,000 tons. And Bell said, what? What did you say? Bell said, at the Treasury Department, we don't talk about silver in terms of tons. We talk about it in terms of troy ounces. How many troy ounces are you talking about, Colonel? And Nichols said, well, I don't really have any idea, but I'll find out for you. And later he went back and he told him, talking about something like 300 million troy ounces of silver. They ended up borrowing not 5,000 to 10,000 tons, but 14,000 tons of silver from the West Point Depository up in New York, and arranged a very secret means. They got some dummy corporation to go up there in trucks, and they got all the silver out, and they got it all weighed, and they carted it off to some other company, and they rolled the ingots into long strips, and then they sent it all up to Alice Chalmers in Milwaukee, Wisconsin. And they turned it into strips and wires and bus bars and so on to make all these windings. And the whole Y-12 plant was just full of this 14,000 tons of silver. And after the war, it was all taken apart and taken down. K-25 proved very, very successful, so that a year after the war, Y-12 was shut down completely. The alpha calutrons were all shut down in September, a month after the end of the war. But the beta calutrons ran again for another year. And then they were all shut down. And all the silver went back to the Treasury. And Groves was very proud. In his book, he brags about 99.96 or something percent of all the silver was returned. They even kept track of all the shavings and all the machining and so on. But that's part of an interesting sidebar on Y-12. But the Y-12 operation really, they had troubles, as I said, right at the beginning, and then all through the spring of 1944, there were problems. I came as close as I ever came in my life to getting fired in late February of 1944. As a chemist, you can't believe it now, but I was a foreman at that time. I was still just a kid, but I'd had a whole lot more experience than any of these people who were working for me. And my boss came to me one day late in February and said, we're getting what's probably the first production batch, and it's extremely important that it be done very, very carefully. We want it to be very pure, but we want to be sure that we don't lose any of it. And we don't want to lose any days, any time. And I said, oh yeah, sure, I'd be glad to. And so I took care of the extraction, the purification, and the conversion to tubenyl oxide, TO3, nice lemon yellow powder, precipitate, and put it in a Buchner funnel and filtered out all the hydrogen peroxide and other stuff. Anyway, then I had to put it in the Buchner funnel in an oven to convert it to UO3, to dry it out completely from UO4 to UO3, TO4 to TO3. And so I put it in a stainless steel beaker. We had carried everything around, anything that anytime you put any of this precious stuff in glassware, you put it in some stainless steel container so that if by any chance it broke, you saved it. We didn't want to tear up any concrete or any more concrete than we had to. This stuff was precious. The stuff that went to Los Alamos in 1945 cost us over $200,000 an ounce. This stuff was precious. So I put it in this stainless steel tank, and I put it in this oven, and I said, well, that's that. It'll be cool in the morning, and I'm going off on a date, so I did. I took off about 10 o'clock, went off to the rec hall, came in the next morning, and somebody saw me coming into the building and said, boy, he said, you watch out for the boss. He's looking for you. I said, what in the world's the matter? He said, there was something terrible happened last night. I don't know what it was, but they're looking for you with an axe. And I couldn't believe what happened, so I just charged into the boss. I just went to his office. I said, what in the hell happened? And what happened was that the stainless steel container had expanded when it got hot in the oven. And then when the glass funnel had sunk down into the thing a couple inches further. And when it cooled off in the morning, it contracted again, but this time it crushed the glass. So here this precious 200 grams of stuff, the first slightly enriched material from the Y12 calutrons, is all mixed up with ground glass and shards of glass, and it's in the bottom of this damn beaker. And of course, the only way you can get it all out is to pour it all out, but then you've got to rinse it with acid, and so you have to go through the whole. So they lost about 2 days. They had to repurify it, redissolve it, repurify it, reprecipitate it, and so on. And my boss told me, he says, Al Ballard told me to fire you. It was his boss. He says, get rid of that guy. He said, just stay out of his way for at least a week or two, will you please? And I said, I sure will. And that's as close as I ever came to getting fired. But that was early in 44, and Los Alamos was desperate. Of course, they're a long way from a bomb. They were desperate to get pure 235 so that they could make their cross-section measurements and pin down even better what the critical mass was going to be, what they had to do to design a bomb and so on for their research. But that all got straightened out, and by 1945 things were going very, very smoothly. At Y12, the alpha units were all working. The beta units were all working. The chemistry cycle was going well. And we started sending weekly shipments to Los Alamos. One of the things that was curious about Y12, really Oak Ridge, was that these rail cars came in every week. The Louisville National Railroad people kept wondering. One time they went to Colonel Nichols and they said, Colonel Nichols said, we just don't understand this. Said we send in 3,000 rail cars full of materials, steel, chemicals, everything, every week. He said, they go out here empty. He said, one of these days, you're going to want to start shipping out, and I hope you call on the L&N Railroad Company to have some of that business. And Nichols said, oh, of course we will. He said, there's no question about that. He said, we'll certainly call on you. People in the town were curious. 73,000 out of the 75,000 didn't have any idea what was going on. What they were very much aware of was that it was a terribly important war effort, and they felt like they were really a part of it. And we kept being told that the Army kept that message coming to us in various ways, reminding us about the war news and how important it was that we keep working as hard as we can and so on. And starting in 1945, they really souped up the message that we need to work hard, because they could see that in January, I guess it was, Oppenheimer and Groves and Nichols went to Vannevar Bush, and they told him that they thought that we would have enough material by August. And so the heat really came through. Now, I didn't learn this until just the last 5 years, but all I heard was out at the WWII was, we need every milligram of enriched uranium, whether it's 15% or 20%. And you scrape the bottom of the barrels. We went back all through that spring, chemists, we went back to barrels that we had wiping rags, diapers. We used diapers by the gazillion to wipe lab benches and so on. We went back, we burned diapers, we burned our lab coats and so on that had slight contamination. And then we would extract these residues just to get back everything we could. We even drained the water off the roofs. We had a 3-inch layer of water on top of the roofs. We had no air conditioning, but the engineers built roofs with built-up sides and could flood them with water, and the evaporation of the water kept the buildings a little cooler. And these are production buildings, and that every bit helps. We used fans, of course, open windows and everything else. But the laboratory hoods inside the buildings, we had them blowing down on that water. And we even siphoned the water off the roofs and boiled it down to recover just a few milligrams. I worked in the chemistry building, I told you to start with, 9203. But in 1 year, we were outgrown. Production rates were much higher, so we had to build another building, 9206. And that building had this roof with water on it. And I remember in the spring of '45, when the orders came out to get everything we could finally possibly get and prepare it for a final product. And we ordered a maintenance truck to come up there. And we didn't have any drains built into the roof. Nobody had thought of that. So we used big Tygon hoses and start a siphon and fill it up with water and run it down to a tank truck on the ground so it would suck the water off the roof. And of course, if the guy up there is holding the siphon just wasn't real attentive, one corner would come up and it would suck air. If he got the hose a little bit out of the water, and you'd have to fill it up and start all over again. Pain in the butt. This maintenance guy, who's some fine local Tennessean, nice guy, I'm not denigrating Tennesseans. My wife would make sure I didn't do that. Anyway, the guy says, look, I know how to stop this. He said, this got all these gravels on the roof. He says, I'll just dig a hole in the gravels, and then all the water will flow in there, just like it does at my sump at the house. And then the water will go in there. I'll stick my hose down in that hole, and that way we won't have any more of this problem. So the next time the thing broke, he lays the hose over here, and he picks up a pick, and he goes whacks at the gravels with his pick. This is a build-up roof. And all of a sudden, About the second time he hits this thing with his pick, there's a hole right square down into our record center in 9206. I'm in my lab down the hall, and I hear this screaming and hollering all of a sudden, a bunch of women screaming, and this sounded like Niagara Falls is coming in. There's 15,000 gallons of water right down on into our records room, and these gals come pouring out of that records room in the front hall, and water all over the place. And that was the day that we'll never forget. We dumped the water off the roof into the middle of 9206. But all through the spring 1945, the product came out of the beta calutrons and went to Los Alamos. I said that nobody ever saw any product going out, and the reason is that the product went out in a briefcase every week. Just a businessman's attaché case. There was a wooden frame, just about that wide, with 2 holes in it, and the precious uranium product was in a container about the size of a coffee cup. The container was built out of nickel, machined out of nickel with a very heavy gold plating inside, not for nuclear purposes, but to make very sure that there wasn't any contamination of the uranium compound. It was UF4, Tuballoy tetrafluoride, UF4, which would make it very easy for Los Alamos to just reduce it directly to metal from UF4. That's the easiest way to make the metal. So we converted it to uranium tetrafluoride, and it may have some residual hydrogen fluoride in there from the process, and that would attack the nickel maybe and get some nickel into it. So that's why it was gold plated. And then it had a nice cap that screwed down on it, and there 2 of these were put in an attaché case and chained to the wrist of a military security officer in plain clothes, and with 2 plainclothes assistants, he would get on the train and go to Chicago and then get on the railroad to Lamy, New Mexico, Santa Fe. And of course, as the summer went on, there might be a couple of shipments of that a week. It's a pretty green crystalline compound, UF4, very pretty, teal colored crystals, kind of look a little bit like some colored sugar that you might decorate a cake with. Very pretty stuff. It's radioactive, but it's entirely harmless radioactivity. It's alpha radioactivity. The material that came out of the Y12 beta calutrons went to Los Alamos, and they turned it into metal parts and machined it into the parts needed for a gun type assembly, where you fire a uranium-235 bullet down a gun barrel into a uranium-235 target. Each one of these are subcritical masses, but together it's very supercritical, and you start a chain reaction which results in the atomic explosion. And the parts went out in July of 1945. Most of them, the gun barrel and most of the assembly for the little boy bomb went out on the cruiser Indianapolis, starting the same day that the Trinity explosion took place in the desert at Alamogordo. And the remaining few pieces that were necessary for the Little Boy bomb went out by airplane and got there July 26th. The whole assembly was ready on August the 1st, and weather delayed it until the delivery of August the 6th. The K-25 plant started operation in early spring of 1945, but the enrichment concentration by June was just up to 7%. But they did send a lot of their material, 7% enriched, with the help of S-50's material. They sent it all over to Y-12 during the spring. And so they made a contribution to that first atomic bomb. Y-12, of course, just used it as enriched feed for their calutron. And every bit of the material that went into Little Boy came through the beta calutrons at Y-12. But the K-25 process during 1945 was surprisingly successful. Groves was just very pleased. It turned out that all of the worries about the barrier plugging and so on that everybody had, it turned out that it worked out just fine. And the process worked very smoothly. Because it was a continuous process, Farlow, instead of 22,000 people, in the next year or two, they were doing their process with 10,000, and then another year or two, it was down to 4,000 or 5,000. So the cost was less than 10% of what it was at Y-12. So Y-12 then shut down their alpha calutrons, the 864. In September of 1945, and that started a layoff of 10,000 people. And then in another year, K-25 was producing 80% pure stuff, and they shut down the rest of the calutrons. So in over a year, Y-12 laid off 20,000 people. I was one of the 2,000 that was left, and it was a traumatic time for Y-12. We didn't know what we were going to do, but the way things worked out, we got a brand new mission in 1947 and been at it ever since at Y-12. And K-25, of course, ran full blast for another 20 years. So that's sort of the way the picture developed. Y-12 in the early 50s got a second Manhattan Project mission of separating lithium-6 from lithium-7 for the thermonuclear project. And so their employment really picked up. We had another banner mission, and it successfully accomplished in the 1950s and 60s at Y-12, and Y-12 has been a major part of the national nuclear defense system ever since. You asked about the girls at Y-12. What that story is dates back to the earliest days of Y-12 operations with these 864 alpha calutrons and the beta calutrons. And the question was, well, how are you going to operate these fancy complex physics machines that I described? Electrical marvels, heaters, you've got to heat this source material to just the right temperature, and then you've got to have these electron beams so many amps going here, and then you have to have accelerating voltages, so many minus voltages here, so many plus voltages here, then you have to have shims on the magnet. All of these are very fancy controls, ammeters and so on and so on. And Lawrence's position right from the beginning, he told Groves that one of the big problems with the calutron process is he didn't know where we were going to get all the PhDs that we need to run these machines. Because out in California, you see, these physicists are tweaking all the time. They're tweaking these magnets, the shims in the magnets that control the focusing of these beams. They're worrying about space charges, and this is a thing for a PhD physicist. And Tennessee Eastman, though, came in, and they said, look, this plant is not going to operate if we run it that way. We can't run this as an experiment. What we've got to do is to run this thing as an industrial plant. And so on this meter that has microamps, on this meter that has milliamps, on this one that has kilovolts, instead of writing a manual that says that you keep the kilovolts between 16 and 28, if the microamps down here are between so and so and so and so. Instead of all of that stuff, how about a different approach? And we put a grease pencil and we mark a red line on this meter, and you say this is knob A, it controls meter A, and you turn this knob A until that's the needle on the meter is up at that red line. And Groves, I mean, the physicist says, oh, you just don't understand how that works. And so that's the short story. But what happens, you see, then, is that they finally said, we'll settle this. We'll just run a test, and we'll take this group of 5 calutrons, and you put your best physicists on them, and you run it for a week. We see how much stuff we get out. And we're going to take 5 calutrons over here. We're going to take high school girls. We're going to put lines on these meters and say, you turn knob A to keep this thing here. You turn knob B for meter B, and so on and so on. And after a week, the girls had won hands down in terms of productivity. And so Tennessee Eastman hired high school women and trained them how to do it, but it was a operational training, you see, rather than trying to understand how the calutrons worked. And it was very successful.